We're never going to stop exploring the unknown in air and space.
We have ignition and we have liftoff.
Response was normal also.
Now that's what we call long-lasting. Even though the two Voyager probes have been traveling through space for 47 years now, their groundbreaking research mission is still in full swing. As is well known, the identical sister probes have now even passed the boundaries of the solar system and recorded a series of mysterious discoveries that leave even the most experienced astronomers open-mouthed. But what undreamt-of structures really lie dormant in the depths of interstellar space? And what about the extreme magnetic wall that one of the two probes detected? Well, these questions are probably just as exciting as the incident that occurred in October 2022. That was when Voyager 1, which had already been traveling in space for 45 years, was hit by the most powerful gamma ray burst ever recorded. In the same breath, however, the primal force of the spectacle also embodied a cosmic mystery. The outbreak and its afterglow simply did not fit our current models, and the experts were consequently confronted with an impossible event. From today's perspective, it seems almost comical when Voyager 1 and 2 plunged into the vast expanse of space on August 20th and September 5th, 1977. Nobody suspected that this was the starting signal for one of the greatest success stories in space travel. No wonder, after all, the originally predicted mission duration was just 5 years, and the probes were actually only supposed to collect new data about the outer planets of the solar system and their moons, which had so far remained largely unexplored. But after the spacecraft had taken the first and, in some cases, unique images of Jupiter, Saturn, Uranus, and Neptune, NASA decided to extend the mission and let the Voyager probes fly to the edge of the heliosphere. No sooner said than done, with a few decades of waiting. While Voyager 1 reached the Sun's protective magnetic bubble in 2012, its sister followed 6 years later. Never before had a man-made object penetrated so far into space. In numbers, this means that the spacecraft have now put an incredible distance of 24.8 and 20.7 billion kilometers between themselves and the Sun. Conversely, the probes also gave Earth-based scientists a unique opportunity to study the extreme edge regions of our home system at close range and to directly explore how our Sun interacts with the particles and magnetic fields outside the heliosphere. However, since Voyager 1 had already reached this uncharted world 6 years before Voyager 2, experts were all the more eagerly awaiting the arrival of the second twin probe to compare the previously collected data with the new information. And indeed, the comparison immediately revealed a surprising similarity. While the experts had previously assumed that the heliosphere was asymmetrical and had a shape that extended far back, the data from the Voyager probes suggest that we are dealing with a symmetrical, or, in other words, round, structure. But the differences in plasma that were registered were all the greater. Before entering the heliopause, in other words, the outermost boundary of the heliosphere, Voyager 1 had detected a strong decay of the plasma currents, while the passage into the interstellar medium was characterized by strong turbulence in the surrounding plasma. Based on this, the researchers suspected a thick but unstable boundary region. But the case of Voyager 2 was quite different. On the one hand, it took just half a day to cross the heliopause, and on the other hand, it was not confronted with the extreme plasma tides that its sister probe had encountered. In other words, the heliopause presented itself as stable and thin this time. But what is it actually made of? Well, the experts point to the influence of the Sun. Since Voyager 1 encountered the heliopause during a minimum in the solar activity cycle, it can be assumed that interstellar magnetic fields and cosmic radiation penetrated deeper into the boundary region of the heliosphere at that time. The strong phase of activity that accompanied Voyager 2's passage, on the other hand, may have stabilized the heliopause in combination with the strong solar wind, a huge magnetic wall. However, this was not the only thing that Voyager 2 was supposed to discover in the outskirts of our home system. Where the probe detected something that had already been predicted on paper, The enthusiasm among researchers was boundless because, apparently, there is indeed an extensive magnetic wall on our side of the heliopause, which acts as an additional protective shield against cosmic radiation. In detail, the magnetic field in this cosmic barrier was stronger than any other magnetic field measured in the heliosphere to date, and it appears to be extremely dynamic in nature. Experts say that the solar magnetic wall is created by magnetic currents moving in the direction of the heliopause, where they finally subside and flow sideways. When the magnetic field direction of our host star reverses in the next activity cycle, this process starts all over again, but this time with opposite polarity. So far, so insightful. And yet, we must not forget that we are still a long way from having decoded the mysterious expanses of the heliopause and interstellar space. While the Voyager data suggests that the outer region of the solar system and the interstellar medium form a complex system, we are still only at 2 points in this colossal system. In view of this, experts insist that follow-up missions are essential for a more revealing overall picture. However, this is still astronomical future music. But if we look back at this point and visualize the technology with which the Voyager probes have achieved their breathtaking milestones, their tireless efforts become even more astonishing. Since said technology is now the state of the 1970s, it can confidently be described as dusty. You just have to realize that if you have a modern smartphone, you have a device with a memory capacity 1,000,000 times greater than that of the Voyager probes. Furthermore, the transmission data of our modern mobile phone connections is almost 40,000 times higher than that of the two old probes. However, the fact that even the most robust technology from days gone by eventually reaches its limits is demonstrated by recent developments. While sudden contact interruptions are now almost part of Voyager's daily routine, NASA has been pursuing a strict power-saving plan for several years that is designed to extend the probe's lives. In detail, more and more components that are not essential for the operation of the spacecraft are gradually being switched off. In the case of Voyager 2, this most recently affected the plasma sensor. Conveniently, Voyager 1's required measuring instruments were still active in October 2022. So it was the first to report to scientists on Earth a primal spectacle that caused a proverbial earthquake in the ranks of astronomers. The most powerful gamma-ray burst ever recorded. When Voyager 1 was speeding through interstellar space, its instruments sounded the alarm. Its systems did indeed report an inexplicably large influx of high-energy radiation, and, if you like, the probe acted as a harbinger of an unimagined spectacle that was to hit Earth 19 hours later. In detail, the recorded gamma radiation was so intense that almost all of our observatories, including NASA's Swift and Fermi telescopes, were instantly oversaturated. It soon became clear that we were dealing with the effects of a gamma-ray burst without precedent, which would subsequently fill an entire special edition of the journal The Astrophysical Letters. Reverently dubbed brightest of all time, or BOAT for short, and given the scientific name GRB 221009A, the record-breaking event immediately raised a fundamental question. What on earth had triggered the extreme eruption? After all, we were dealing with a spectacle that had an energy of 18 tera-electron volts and consequently shone 70 times brighter than any previously observed eruption. But that was by no means all. The eruption also produced a rather strange jet of radiation that pushed the current models of the afterglow of such events to their limits. More specifically, the astronomers uncovered a new component in the radio range of the jet that left them completely baffled. But other ranges of radiation also exhibited strange anomalies. Among other things, the jet appeared to be unusually strong and focused. In April 2024, astronomers were finally able to identify the origin of the record outburst, but the bottom line was that this finding only raised more questions. The radiation, which was so intense that it even altered Earth's ionosphere, did not come from a colossal mega-explosion but from an astonishingly normal supernova, at least, This is what follow-up studies with the James Webb Telescope's high-resolution near-infrared spectrometer showed. But how can an ordinary stellar death set in motion an event that, according to researchers, occurs on Earth only once in 10,000 years? Well, that is precisely the question, but one that has yet to be answered conclusively. In principle, however, astronomers suspect that the extreme gamma rays could be related to a special form of explosion. As soon as rapidly rotating massive stars collapse, they generate bundled particle jets that race through space at almost the speed of light. If these jets are particularly narrow and concentrated, they produce a particularly bright, high-energy beam. Since the jet of the record outbreak also had one of the narrowest jets ever recorded in a gamma-ray outbreak, scientists believe that the energy in the supernova could have been concentrated in a very similar way. The background to our jets, however, is much less mysterious.